Hello everyone, my name is Roger Fari and I would like to welcome you to another video of data mining series. In this video, we are going to switch gear from supervised dimension reduction to unsupervised dimension reduction. And specifically, we are going to talk about a very famous dimensionality reduction method called principal component analysis. So let's look at the slides. Alright, so we start off this video by seeing the difference again one more time between the supervised and unsupervised dimensionality reduction. After that, we'll talk about what is principal component analysis, and of course we're going to look at two examples, one very small example, toy example, and then we'll look at a real example that how PCA can be beneficial for as far as an analytic method. So as we discussed, supervised dimension reduction is when we do the dimension reduction by the goal of making sure that the classification or prediction task, which is basically connecting the independent attributes to a dependent attribute, is going to be the most successful it can be. Basically, we find the best subset of independent attributes that we can successfully classify or predict a dependent attribute. But, against it comes unsupervised dimension reduction. What is we are going to learn today in this video, there is going to be a general dimensionality reduction to reduce the number of columns and attributes by making sure that we are keeping the most important or the part of the important from the data, but at the same time reduce the number of attributes and the dimensions. One of the methods that is very famous in this arena, unsupervised dimension reduction, is principal component analysis. Principal component analysis is basically a mathematical technique that basically transforms the data by transforming the correlated dimension by transforming the axes in such a way that the dimensions, the new attributes, which we call PCs or principal components, are uncorrelated, and at the same time the most amount of variations are explained by the first few PCs. Something that we'll see what we mean by that in the examples that we'll see. And one other thing that we'll discuss once we see a parametric data dimension reduction better is that PCA is non-parametric data reduction. So just, at this point, take it from me that it's non-parametric data reduction. Once we see an example of parametric dimension reduction, I will come back to this point and we'll discuss that and we will understand it better. Alright, so let's look at our example. So this is a toy data set. I mean, it's a very simple data set. It's been created just for the purpose of understanding PCA. We've got two dimensions and we've got 20 data objects, and all those 20 data objects are shown in this scatter plot, right? We also see other stuff here. We also see, the amount of variance or the amount of variation in dimension 1 is 415 and the dimension 2 is 611 and the total variance is 1026. We also see that there is a correlation between the two varied dimensions. I mean, we do see that correlation and relationship, which is 0.85. After we apply PC, this is what we get. We transform the data, and once we transform it, what will happen, we're going to have two new transformed dimensional attributes. We call them principal component 1 and principal component 2. You can see here that as the definition of PCA, the attributes or the dimensions have correlation of 0, right? This is a very small number, and we can see that there is no relationship between them. But what is really important here to pay attention here is the fact that the total amount of variance in the data between the toy in the original data and this data does not change. right? Pay attention to the total amount of variance. They are exactly the same. So what we managed to do using PCA is to transform the data in such way that most of the variation in the data has been pushed to PC1. Look at how much variation it's carrying now, 957. A lot of variation from dimension 1 has been pushed to dimension 2. At the same time, PC1 and PC2, they do not have any correlation, or they are orthogonal to one another. So that's basically what PCA is doing here. I mean, these two things. But from a visual aspect and also looking at the data, if we pay close attention, we can see that actually the original data is basically a rotation, or the transformed data is a rotation of the original data. So let me sort of like rotate this figure like this by some degrees. Once I do that, you will see that this is the same data, right? I mean, every point you see here, you can find those points on the other one, right? So this is basically the same data that we are looking at here, but we've just transformed it. So basically that's what PCA does. It rotates the axes, and it does it in such a way that in plain English, so let me get ahead of myself a little bit here. In plain English, the new components have the most of variation, and at the same time, the correlation between these new attributes or these new dimensions is 0. But there are a few other things that I would like to explain about PCs before we get to the real example. There is a concept of variance explanation, or explanation of variations. By that we mean that every data set has a total amount of variations that these attributes are showing in the data. It doesn't matter that these attributes are whatever they have. What matters for us is what are they varying, what is the variance that they're showing across the data object. So that's the information that we have from each attribute. So when we transform the data, we transform it in such a way that the most of the variations are explained by the first few PCs. And that's basically what PCA does. So look at this comparison here. We had around 40% variance explanation for the dimension 1 in original data, but we managed with PCA to push most of the variation to PC1, and now we have 93.24% of the variation in PC1, right? So with two attributes, we could show 100% of the variation, but having them PC, we can cut the number of attributes by 50%, at the same time keep 93% of the variation, or 93% of the information in our data, which is a pretty good sort of like a compromise. If it's really important for us to have a reduced number of data, the reduced number of attributes, then we make this compromise by letting go of some of the information, but at the same time keeping most of them, at the same time having less number of attributes. So now let's go ahead and look at this one caveat that you want to pay attention to every time you are about to use PCA, and that is, if before doing a PCA on a real data set, you want to have a standardized data set. And if you don't know, there is a difference between normalizing your data and standardizing. Normalizing is when you make sure that the scale of all of your attributes are the same. To normalize, you would do something like this. You would say, the new data is equal to the original minus the minimum of the attribute divided by the maximum minus the minimum of the attribute. And if you did that, then your new attribute will be between 0 and 1. And because the scale is the same for all of the attributes, when you use a clustering algorithm that uses these values for finding the distance between data object, then each of these attributes will carry the same weight. But for PCA, we want to standardize the data, and when we standardize the data, we use a formula like this. We say nu is equal to the original minus the mean or the average of the attribute divided by the standard deviation of the attribute. And when you do this, you make sure that the variance of your new attribute, the variance or the standard deviation, will be equal to 1. As you saw, what PCA does, it pushes, by changing or rotating the axis, it pushes the variance around, right? So if one attribute has a large amount of variation over the other attributes, just because there is more variation in that attribute's variation is gonna become more important. And the variation is not just the variation is about the attributes varying. It's about because the scale of the attributes is larger, therefore the variance is higher. That's why every time we do PCA, it's a really good general recommendation that you can follow every time, is to standardize your data before doing PCA. But anyway, let's move on to our real example. Of course, this is a standardized data. You can see that the values have negative and positives because it's just been standardized. And when you have a standardized data, the mean of the data will hover around 0, and you will have negative and positive values. But anyway, this data set shows the happiness indices of 122 countries for 10 years. So we've got 9 happiness indices, and we've got 10 years from 2010 to 2009, and we want to sort of like understand the patterns of these happiness indices around the world between these 122 countries. Of course, one approach we can have here, it would be to go about and do some clustering analysis. I mean, when we do clustering analysis, of course, we have to find the number of clusters. We do all of that, and we will actually learn how to do that in one of the future videos. But what you will get in the end of a clustering analysis is basically this. It says, okay, this cluster 0, these are the countries. Cluster 1, these are the countries. Cluster 2, these are the countries. And of course, you could do some central analysis, something we'll see. But that, as far as it goes, as far as what is the variation in the data. Another approach would be to use PCA, right? And when you do sort of like apply PCA on the standardized data, you would see for this specific data, using the first 3 PCs, PC1, PC2, and PC3, you will be keeping 71% of the variation in the data, right? Instead of having to have 90 attributes, you can only have 3 attributes, and use those 3 attributes to carry 71% of the variation in data. That's a pretty good deal. And once we have only 3 attributes, guess what we can do? We can visualize. Now we can visualize, because we only have 3 attributes, and we can show something to a decision maker or for ourselves, creating for ourselves, to see the patterns in the data. So we can just go ahead and create a scatter plot, x-axis PC1, y-axis PC2, and color PC3. But when we are looking at this figure, as amazing as it is, and it's amazing that we see what's happening in sort of like 90 attributes only with one visual. But at the same time, we have to sort of like put our effort to don't forget that PC1 is carrying 74% of the variation, actually more than that. It's carrying around 60% of all the variations shown in this figure, right? How do I calculate that? It's, the 47 divided by 71, right? And around 20% is being carried by PC2, and the rest is being carried by PC3. So we have to understand that the fact that PC1 these points are further apart is more important than PC2, and we sort of like can think about this and like sort of be keeping in the back of our mind, or we can do some visual guides like this, right? So with these visual guides, we are sort of like showing to our audience that the distance of PC1s are more significant. I mean, a little bit of distance is more. I mean, this amount of distance for PC1 is equal to this amount of distance. We are carrying that over to our to the person who's watching this, and also we sort of like try to have a less pronounced PC3. If you pay attention here, it used to be between -6 to 8. Now it's between -9 to 9. It's sort of like make the color less pronounced. And these values are calculated by some relative relative calculations of numbers to go with these percentages that you can calculate from here. One thing we can do next is to annotate this scatter plot. Of course, each of these points is a country, and when we annotate them, now we can take advantage of this visual by looking at it as sort of like seeing the patterns in the relationship among these countries. I mean, you can see I haven't annotated all of the countries because I wouldn't want the visual to be too cluttered. So I've annotated some of them. So by looking at some of the countries at the same time, where they are next to other countries that they have named, now it starts to give us some insight about what's happening in the data, and that's achievement, because now we have a visual representation of 90 attributes, and we can sort of see what's happening and who are the countries that are closer to one another and who are the countries that are further apart. And that's a pretty good achievement. And this is what we get when we have PCA versus clustering. Clustering is that these countries are in one cluster. It's sort of like cut and dry response, which could be excellent because when we want that cut and dry answer, but when we are more open to fuzzy answer, we want to sort of like see what's happening, that's what we want, then it might be PCA for dimension reduction to give us a visualization might be a better route to go. Before finishing this video, let me talk about the importance of standardization. I mean, if you look at the original data with 90 attributes, the attributes such as healthy life expectancy had such larger variance and variation than other attributes. I mean, you can see that these would basically become what the PC1 and PC2 would show if you didn't take care of the standardization of your data. But when you do standardize your data, all of the attributes will have a fair chance to sort of like be a part of that PC. The information of all of the attributes or the variations of all of the attributes will have a fair chance to be a part of those PC1, PC2, and PC3. And before, one last slide. I mean, I promise this is going to be the last one before we get to the summary. We did talk about, in previous videos, talk about supervised dimension reduction. Now that you have seen an example of unsupervised dimension reduction, you did see that we didn't have any goal other than just reducing the number of dimensions, and we didn't want to get a specific answer or make a classification or prediction more successful. It was just done by the inherent patterns in the data, and we basically managed to find the sort of commonality by using the PCAs. And instead of having to use 90 attributes, we used 3 attributes, but we had to let go of some of the variations in the data. But if you remember, the supervised dimension reductions such as decision tree, linear regression, random forest, computational dimension reductions, all of them, we always had a goal in mind. We wanted to make sure that our classification or prediction tasks are more successful. So now these two terms, supervised and unsupervised, sort of like making more sense. All right, let me try to offer a summary of this video for you. So in this video, we did talk about twice, the distinction between supervised and unsupervised dimension reduction. And now it's making much more sense because we have seen examples of supervised dimension reduction in the previous video, and in this video we saw an example of unsupervised dimension reduction. And of course we talked about this very famous method of unsupervised dimension reduction, which is principal component analysis. We saw what it is using a toy example, and then we saw how it could be beneficial using a real example. Until the next video.